Welcome to the last in our work sampling video series. This is going to finish up the example problem that we started in the prior video. So just as a reminder, we have machine as the subject and we have these three categories. The example I'm going to go through, I'm going to use the category machine idle to do the first round of analysis for this work sampling study, and then I want you to practice doing the same analysis for being set up and running production after we go through the numbers. And so we had 500 observations. We found the proportion of time the machines are spent in each operation, and you're going to bring some analysis and thoughts about these questions when you come to class, and we'll go over this problem, as well as going over the setup and running production categories that you're going to analyze yourself for practice. So we ended the last video saying that we have a confidence level, 95% confidence level, that the idle time is between 21 and 29%, and I'm going to go over and show you the calculations of how to do that now. And remember, the confidence level is something we set going into the study. It's not something we need the data from the study for. It's something we set going into the data. However, the accuracy of the study is based on the information on the data collected in the study, and we'll go through that calculation. And additionally, we'll go through, if 500 observations doesn't give us 99% accuracy, then how many observations do we need to take? And then we'll also talk about conclusions and recommendations we would make as a result of the analysis that we've completed. So let's look at the problem first. So we have, we're going to complete the analysis on idle time, on the category of idle time. Again, the 95% confidence interval. If those of you that are familiar with statistics, you'll know from looking at the tables that 1.96 is actually the value that we would use. However, to be consistent with the video and ease of calculation, we're going to assume 2. And this represents the 2 standard deviations away from the mean that we saw on the slide in the PowerPoint. And so how we get our confidence interval, so we were going to be confident that we have 95% of the population and that our true idle time is within this interval that we have. We take our proportion that we calculated from our study data, and the little hat just means that it's an estimate. Then 2 is because of the number of standard deviations away from the mean, because we're basing it on a confidence interval on 95.4% confidence. So we've got 95.4% of the population within this interval. If we wanted only 1 standard deviation, then this would be 1, and we would only have 68% of the population captured. So again, 2 is going to be the common, but it's something that we determined going into the study. That is then multiplied by the square root of the estimated proportion, for this case is going to be idle time, times 1 minus the estimated proportion divided by n. And notice I've got it a capital N here. This is the number of observations for the study as a whole, not just for idle time, but the number of observations for the study of a whole. So as you can see, it's 500. That's going to be the lower bounds of the confidence interval. And we know that our true idle time, if we were to watch 7 by 24 for 100 years, would be, we'd be 95% confident that it's within this interval, because we've captured 95% of the population. And then the upper bound is the proportion idle that we got from our study data times 2. Again, this is related to our 95% confidence interval that we determined we wanted coming into it, times square root of the estimated proportion times 1 minus the estimated proportion divided by n of the n number of observations in the whole study. Now this piece right here is what our absolute accuracy is, and really it's what our error is, but nomenclature for work sampling analysis says this is accuracy, but I'll just call it error from now on, and then 1 minus this error is what our accuracy level of the study is how I'll discuss it going forward. So if we go through and figure out our confidence interval for the idle time, we know that our idle time is somewhere between 0.25, because that was our proportion of idle from the study analysis, minus 2, again our 95% confidence interval determines that this is a 2, times square root of 0.25, our proportion of idle time, times 1 minus 0.25, which is 0.75, divided by n, 500, our total number of observations in the study. And our upper bounds is that exact same calculation, but instead of minus 2 times the square root of estimated proportion times 1 minus the estimated proportion divided by the number of observations in the study, it's +2. So if we go through and do that calculation, we see that the upper bounds is 28.9% and the lower bounds is 21.1%. So I can say that I'm 95% confident that the true idle time for this machine set lies somewhere between 21% and 29%. I'm doing a little rounding there, okay? So that is my confidence interval. I'm 95% confidence that idle time is somewhere between 21 and 29%, okay? Or I've captured the idle time is somewhere between 21 and 29%. And then our accuracy, again, AA means absolute accuracy, but I'm going to say this real error rate is just simply this piece of it right here, the 2 times square root of the estimated proportion times 1 minus the estimated proportion divided by the number of observations, and this is 3.8%. So we can say our error rate, error related to the idle time is 3.8%. So you can see if you take 25%, which was our percent idle time, plus the error, that gives us the upper bound, minus the error gives us the lower bound of what that is, okay? Now, we can't say that the whole study has an error of 3.8% because we need to figure out what the error is on the other categories, which I'll let you figure out on your own, and then we'll talk about what is the accuracy of the study overall. So the accuracy of the study overall is going to be, I like to think about it in terms of a chain is only as strong as its weakest link. A study is only as accurate as its least accurate category. So we'll see what that is. Discuss it when you bring the other 2 categories to class. All right, so now we want to say, now we know that we have a 3.8% error, which means really our accuracy is roughly 94%. 1 minus the error would be our accuracy, right? So 94%. And what the operations controller wanted was a 99% accuracy. So only to have this error be 1% instead of 3.8%. So how many observations would we need to take in order to reduce that error from 3.8 to 1%? Well, we can take this formula right here, and you can see it's just a nomenclature here, and we can rearrange it. So instead of solving for accuracy, which we did here to find out the accuracy of the study given the data that we had, we can turn it around and we can solve for n instead to see how many observations do we need in order to get the desired accuracy. And remember, this 2 again is a result of the confidence interval that we want, the confidence interval that we want. It has nothing to do with what the accuracy of the study is. Okay, so again, the confidence interval we decide going into the study, the accuracy is a function of what the data tells us we calculate it to be. So if we want to figure out how many observations we would need to get 99% accurate or only have a 1% error, it would be 4 times 0.25, which is the estimated proportion of idle time, times 1 minus 0.25 is 0.75, divided by our absolute accuracy squared, and which is our error rate, and so that's 1%, so we only want an error of 1% squared, and that equates to 7,500 observations versus our original of 500. So that is a lot more observations. I think it's 15 times more observations. And so would we really want to do that? Is it worth 2.5 points of accuracy, or would we be better off just taking action based on the data that we have now? Remember, the trade-off is we be more accurate, but it's also going to take more time. If we had 500 observations over the course of a week, and remember we looked at how many that would mean per day, it was really kind of a robust set of data. It would be pretty hard-pressed to do more than 500 in a week, and so does that mean we'd have to stretch the study out over 15 weeks? And is it going to be worth it to get that much, the increased accuracy, or would we be better off taking action on the data that we have? I'm going to say we'd take it on the data that we have because that's a lot more information to gather, so it would take time and resources to do that. Okay, so we determined the confidence interval for the idle time, and the formula is up here. This PDF is posted on PolyLearn for you. And then we also calculated the accuracy or the error rate for idle time. And I need you, or would like you, to go through and do the same thing, calculate the confidence interval and the absolute accuracy, really I like to call it absolute error rate, for the remaining categories, and bring it to class and we'll discuss it. Okay, so let's go back to the PowerPoint. We have Now determined how to do this calculation. We see that it takes a lot more observations, so probably not really worth it. So now that we have the data analysis, what are we going to do with that data? What are going to be our recommendations or some actions that we might take as a result of the analysis? So my conclusions were from looking at the idle time is that it's excessive and unacceptable, that we have 25% downtime. And if you look at it in terms of an 8-hour shift, that says 2 hours out of every shift is down. And so I'm just making an assumption here that we have 40 pieces of equipment. And in reality, that's not a whole lot. There's one area that in the factory that I worked in Mexicali where we did assembly and test where we had 200 pieces of equipment. So if it's a large factory, it wouldn't be uncommon to have that many. But let's just say we have 40 pieces of equipment. That equates to 80 hours of downtime, right? 2 hours of downtime per piece of equipment times 40. And so that would be 2 equivalent pieces of machinery. 80 hours, machine hours a week divided by 40 available hours a week. So 2 pieces of equivalent machinery. So if we can reduce the idle time even by 50%, we can either postpone buying another machine and save the capital expenditure associated with it, which I've just made an estimate here, or we can increase our capacity and build more product, assuming we have demand, without having to buy anything. Additionally, it takes labor to run the equipment and maintain it. There is cost in maintenance with extra tooling and spare parts, consumables, electricity, if it takes any water or chemicals, oil, to make the machine run, and then it consumes floor space as well. So all of that would be saved by not having to have additional equipment. We're going to talk about this concept of how to best utilize equipment when we get towards the end of the quarter in something called OEE, or overall equipment effectiveness. So again, that's what the data is telling us. And so then what are we going to do as a result of this analysis that we have and information? So we might complete a Pareto analysis to understand why the equipment is idle. So why the equipment is idle, and then take specific action as a result of that. Maybe make machine wait times, idle times more visual to operators. So that's visual management that we talked about in lean manufacturing, using an andon or audio signal. It could not only be to operators, but to technicians and engineers. Maybe we could increase reduce the time it takes to change over. So the SMED, single minute exchange of die, is a topic we learned about in lean manufacturing. Shorter transition between parts. So this may be going beyond the idle time only, looking at the study as a whole. Improve scheduling of material and people. So if it's waiting on material or people, that it's not anymore because we have it scheduled correctly. Not too many, but not idle and waiting as well. Stagger breaks and lunch, so the machine's not waiting on the operator, so it's not idle because an operator isn't there to run it. And then train operators to resolve common issues. That also would go towards helping with the +1 waste, where we take advantage of employee creativity, make the job more interesting, and raise the skill level of the workers. Okay, so that's an example of the type of data collection, data analysis, and then recommendations that you would be expected to make in a work sampling analysis and in the example you're going to do in class based on your project or some other area. Okay, so that wraps up work sampling. We had the first video where we talked about what work sampling is and that it's a statistical technique to estimate broad categories and figure out where to go work next. In that same first video, we talked about the work study procedure, so the steps to go through to develop a work study analysis and data collection procedure, which you're going to do for your project or other area. Then we had a second video that talked about the advantages and disadvantages of work sampling and how, even though we have it listed as a work measurement tool, it is slightly different and not appropriate for the short repetitive cycles like direct time study, predetermined time standards, and standard data is. And then we went through an example problem. We had a part 1 and a part 2 where we looked at the statistical basis of work sampling and then talked about the analysis, not only numerical, but additional analysis for what our next steps would be. So that wraps up work sampling, and thank you for listening.